I built my own DIY retro game console using a Raspberry Pi Pico 2 on a breadboard. So, how did I pull it off? After days of working on this Game Boy project non-stop, through all the development and building stages, I finally managed to get it running smoothly. Of course, the project isn't completely finished yet. There are still a few missing pieces and improvements I need to work on. If you want to see more DIY projects like this, don't forget to subscribe to my channel and like the video. If you're ready, let's get started and show you step by step what I did in this project. First up, let's start with this breadboard. We'll be using this entire board solely to map out and place our 8 control buttons for the console. I specially chose this 2.8-inch TFT SPI screen to bring this amazing project to life, as it perfectly allows us to play all our favorite classic Game Boy Color games in glorious full screen, without missing a single pixel or compromising on the overall smoothness. Actually, I temporarily used the Pico 2 just to test the walnut framework on this circuit. While the RP2350 processor is fast, its 4 MB onboard flash pushes the absolute limits with such a massive code size, completely exhausting the RAM during display and I2S audio tasks. We'll be using exactly 8 buttons for this project. I'll be setting up and making all the connections for these controller interface buttons right here on the breadboard. We will be using this micro SD card to safely store all of our games. By inserting this card directly into the integrated SD card slot located on the back of the display, we will ensure that the processor has fast and direct access to the game files at all times. And finally, we will use our colorful jumper wires to connect all these hardware pieces on the table together and complete the circuit flawlessly. Now, if everything is set and you are ready, let's move on to the eagerly awaited assembly phase step by step. As you can see, I am sitting down at my desk and getting straight to work to map out the directional pad and all the control buttons for this custom Game Boy console. I am placing a total of 8 buttons one by one onto the breadboard, which will trigger the left, right, up and down functions, alongside the A, B, start and select commands. Actually, I was supposed to add 10 kilo ohm resistors to this circuit for the buttons. However, since the project is currently just in the testing phase, I will proceed without using resistors for now. Still, ensuring the button pins fit perfectly into the rails and remain stable is crucial to prevent any potential short circuits down the line. In this part of the video, to avoid any confusion, we are going to follow a precise 2-stage preparation. The first and most fundamental connection we must make is the common ground line. Since I don't have only black wires on hand, I am using completely random colored jumper wires here. I need to connect one leg of every single button to the negative ground rail on the breadboard. This creates a shared return path for all the buttons, allowing us to complete the circuit. Once we have that foundational step sorted, we can shift our focus immediately to the second stage, the signal wires that will run directly to the Pico. These are the crucial data lines that will allow our code to distinguish exactly which button is pressed. Again, using the mixed wires on hand, I'll prepare one-to-one connections from the remaining free leg of each button to the designated GPIO pins on the Pico. It's going to require a bit of organization for this tangle of wires, but this preparation will make our lives infinitely easier when we get to the programming phase. Now, I'm moving on to another crucial phase of the project. I'm starting to connect the jumper wires, focusing first entirely on the display setup. Since we are using the SPI protocol to communicate with the display driver, this part requires extra attention. Looking closely at the pinout diagram open on my monitor, I am identifying the screen's critical data lines like MOSI, SCK, CS, and DC one by one. Plugging a wire into the wrong spot causes data collision and disrupts the screen synchronization. That's why I'm taking my time, carefully following the schematic to finish this wiring. We've finished the screen wiring, and now I'm plugging in the jumper wires for the integrated SD card slot right on the same board. There is a GitHub link right in the description of this video, so you can download the entire schematic from there. This will give us direct access to our game files. Now, we have reached the stage where we connect all these jumper wires, which we just plugged into the display module, to their respective pins on our processor, the Raspberry Pi Pico. At this point, I highly recommend that you don't rush through it and avoid making the connections too quickly. Plugging the SPI lines or power connections into the wrong pin will prevent the hardware components from communicating with each other, resulting in no display output. Therefore, move forward carefully, step by step by looking at my schematic, provided in the GitHub link down in the video description. Continue the assembly by making sure every single wire matches its correct GPIO pin on the Pico. When you follow the diagram explicitly, we will successfully complete the wiring process without any issues. With the screen done, now I'm moving on to connecting the jumper wires from the integrated SD card slot on the board to the Pico. This part is critical for our game files to load correctly, so I recommend making these connections slowly without rushing. Once again, staying faithful to my schematic available in the GitHub link down in the description, I am plugging each pin into its correct GPIO line one by one. Once we match the lines properly, the wiring will be complete. And now that I have safely plugged all of our complex wires into the Pico, I am carefully inserting the micro SD card directly into this integrated SD card slot on the back of the display. Now we've come to the very last step of the wiring process. I am starting to plug the ground lines and the positive GPIO connections of the buttons on the breadboard onto the Pico one by one. As you can clearly see on the screen, the Pico schematic open on my monitor is being incredibly helpful to me during this process. By looking right here, I can accurately see exactly which pin each jumper wire needs to match up with. Thanks to this visual guide, I am finishing up all the connections in sequence and with full confidence. With that, we finished the hardware assembly. Now it's finally time to flash the Pico with the custom code I've been working on for days to get ready. This software is what will truly breathe life into our console. As you can see on the screen, I am taking my USB cable and holding down the bootsel button on the Pico right before plugging it into the computer. Keeping it pressed, I slide the cable into place. This puts our microcontroller into bootloader mode, making it completely ready to flash the custom software I prepared. I opened the Arduino IDE, created a new sketch, and placed all my code here. I opened the Preferences tab from the File menu at the top, and I am adding this crucial URL link here to introduce the Pico 2 board to the system. Because without this link, the Arduino IDE can never detect or recognize the next-gen Pico 2 processor we are using. For the next step, we open the Boards Manager tab from the left menu. You need to type Raspberry Pi Pico into the search box. As you can clearly see on the screen, this package is already installed and active for me. If you are doing this for the first time, you must click the Install button right next to it to set up the library on your computer. After the board setup, this time we open the Library Manager tab from the left menu. To install our display library, you need to type TFT_ESPI into the search box. As you can clearly see on the screen, this library is already installed and active for me. If it's not installed for you, you must click the Install button right below it to include this library in your system. Now we've come to the most critical step. On the C drive, navigate through your user folder into OneDrive, Documents, Arduino, Libraries, and then the TFT_ESPI folder. Note that the username part will be different for everyone. Open the user_setup.h file inside and directly copy and paste the ready-to-use codes from my GitHub project into this file. Go to the Tools menu and select the port your device is connected to. Then, choose Raspberry Pi Pico 2 from the board list and set the flash size to 4 MB, no FS. And then CPU speed to 200 MHz. And finally, click the Upload button in the top left to compile and flash the code to our Pico 2. I've speeded up this compilation part a bit so that the video doesn't get too long. But as you can see on the screen, everything is going perfectly well. The process is running like clockwork without any errors, and our code is successfully being flashed into the board's memory. The upload is finally finished, and the game list is reflected on the screen. As you can see, all games are right in front of us. From here, I am selecting the legendary Tetris game on our list. The moment I press the button, we see the ROM loading, warning on the screen, and our game loads smoothly. And there it is. Our Tetris game is live right in front of us. The response time of our device, the button registration, and the display refresh rate are absolutely perfect. Thanks to the power of our Pico 2 processor, we can test the game completely smoothly without any lag or stuttering. Of course, Tetris runs completely smoothly because it's a small game in size. However, the Pico 2 has some disadvantages as well. Since it only has a 4 MB flash memory size, unfortunately it cannot run larger games like Donkey Kong or Zelda due to insufficient storage. Now let's test the Tom and Jerry game from our list. As you can see, when we press the button, this game also opens completely smoothly and quickly. Now let's jump straight into the game and see how the controls respond. As you can see, every button press gives an instant response. Our character moves like clockwork, and everything runs beautifully without a hitch. Now that our Tom and Jerry test is a success, let's go ahead and try our luck with a much larger game. And finally, let's try to load the larger sized Super Mario Deluxe game from our list. I'm pressing the button, but as you can clearly see on the screen, the game doesn't even open. This is exactly where that 4 MB flash memory limit comes into play, and unfortunately the system cannot handle these larger games. Right because of this, I went ahead and purchased this specific board from Pico's first generation 2040 series, featuring a full 16 MB of flash memory. Let's unbox it right away and check out the board. Thanks to this expanded storage, we will finally be able to load larger games like Donkey Kong, Zelda, or Super Mario Deluxe without any restrictions. I seriously can't wait to try it out. In the coming days, I will be running all the performance tests and game trials for this 16 MB board. In addition, I will be adding this MAX98357A I2S amplifier module to the project to get proper sound. While running hardware tests, I'm designing a custom PCB that will be the foundation of this project. This green board you see will be the heart of Pygame V1. My main goal is to release it fully open source. I'll make everything from design files to code accessible so anyone interested can easily build their own handheld console. And that brings us to the end of another video. To see the continuation of this project and not miss the next steps, please make sure to subscribe to my channel, leave a like, and drop your thoughts in the comments section. Your support truly means a lot to me.